Okay, go for it. Wasserstein gradient flows at Moreau envelopes of f-divergences introducing kernel Hilbert space. A great title.
Yes, so thank you very much. Hi, everybody. I'm Viktor Stein. I'm a second-year PhD student from Berlin in Gabi's group. And before I move on, I want to thank, obviously, Liu for organizing and Wuchen Li for hosting me here in Columbia and introducing me to the seminar. So you've already heard the title. This is joint work with Sebastian Neumeier from TU Chemnitz in Berlin, and my advisor, Gabi Steidl, and Nico Rux, who just finished his master thesis with us. So in one slide, let's see, what is this paper about? So a very common goal in applications is we have some underlying data distribution that we want to know more about, here modeled as a probability measure nu on RD, but we only have samples available, and we somehow want to recover this underlying distribution. And one way to achieve this is by minimizing some f-divergence, df nu, to this measure nu. For example, the Kohlberg-Leibler divergence, KL. Unfortunately, on the theoretical side, this objective might not be very good as an objective to minimize because, well, we only have samples available, which will model as an empirical measure mu, but this empirical measure mu will not be absolutely continuous with respect to nu, and hence the objective will be infinite. So our solution to this problem is to instead consider a regularized version of this f-divergence defined on all measures, which alleviates this problem. And we construct this regularized version of this functional in two steps. The first is performing some kind of generalized kernel trick by mapping these measures into a reproducing kernel Hilbert space by integrating the measure against the kernel, essentially. And this takes us from the world of measures, discrete or absolutely continuous, or both, and the topology of weak convergence to the space of functions and the topology of pointwise convergence, which is a lot more easy to handle. And using this kernel trick, we extend our functional, the f-divergence, from the smaller space, the measure, to the larger space, the Hilbert space. And we then end up with a convex lower semi-continuous function on the Hilbert space. So we can do standard convex analysis techniques, namely Moreau envelope regularization. What we then end up with is the following. The functional takes the measure, embeds it into the Hilbert space by this kernel trick, and then we apply the regularized version of the Hilbert space version of our functional. And this then takes this nice form. And now we have spent so much time constructing this functional, better have some good properties, and indeed it has. I'll list them all later, but for now it suffices to say that we prove existence and uniqueness of Wasserstein gradient flows of this new objective, which now is always finite, for example, in particular, never infinite. And we also prove that if we start with some empirical measure, which is always useful for applications, the Wasserstein gradient flow will remain an empirical measure. So we can do particle flows, as you can see here on the right. Okay, I will now briefly comment on some prior work in this direction. The main inspiration for our work was this Kale functional defined in this work by Pierre Glaser, Michel Abel, and Arthur Gretton. And what's happening under the hood there basically is they consider an MMD regularized KL divergence. And what we do is extend their work and theory to arbitrary f-divergences. And we also, I made this a bit clear on the last slide, have this convex analysis perspective on this functional, which was not mentioned in this work. Along similar lines, 2 years later, this kernel methods of moments paper by Kremer, Nemur, Shirkov, and Zhu, they consider an f-divergence regularized MMD. But I mean, if you have the contribution of two terms, you have to minimize them. Which one is like the original objective and which one is the regularizer? It's just a matter of taste. So their functional is similar to ours, plus some constraints, but they don't cover all f-divergences and also this They don't have this convex analysis interpretation, which I'll explain later. More distantly related works is this f-gamma divergences by Birel and co-authors. They don't consider Moreau envelopes, but Pasch-Hausdorff envelopes. So essentially, they don't regularize with a squared norm term, but just with a norm. And hence their functional will be only Lipschitz and not differentiable, as in our case. And also related is the Wasserstein 1 Moreau envelopes with f-divergences defined in this paper by Terjek. Big difference to our paper is that there's no reproducing kernel Hilbert spaces in his paper. And for us, they're very important because they make computation amendable, because the optimization problems become finite dimensional, and he has to do other tricks to achieve computability of his divergences. This talk is structured roughly in 6 parts. The first 3 parts will be just a brief introduction or review, depending on your background, of the 3 ingredients we need for our work: reproducing kernel Hilbert spaces and MMD, Moreau envelopes from convex analysis, and f-divergences from information geometry. Then I'll put all these 3 things together into MMD Moreau envelopes of f-divergences, which is the novel functional we defined. Then I'll briefly remind you about Wasserstein gradient flows, even though you probably all are experts in that topic, and then show you what we've proven about the Wasserstein gradient flows of this novel objective, and show you some examples as well. So reproducing kernel Hilbert spaces are the framework in which this kernel trick is usually performed. The idea being embedding data into a high-dimensional Hilbert space, making analysis there nicer. For example, here we are separating red and blue points, and by mapping them into a high-dimensional space, this nonlinear decision boundary becomes a linear decision boundary. This embedding is achieved via such a kernel, K, and this is a symmetric positive definite function. In our work, we restrict ourselves to radial kernels, which are functions phi of the squared norm difference of their inputs. And I'll explain later why we make this restriction. And in particular, we need some smoothness of this kernel. In particular, twice continuously differentiable, and we want the signs of the derivatives to be alternating. Wendland, for example, calls this completely monotone. Once we have such a kernel, this yields in a unique way a reproducing kernel Hilbert space, which is the Hilbert space of functions roughly formed by taking the closure of the linear hull of these kx dot for all x, and its key property is that point evaluation is continuous. Let's see some examples for these functions phi, which then generate our kernels. The most classic one is the Gaussian kernel, in which phi would be e to the minus r and some positive prefactors. It's not r squared because here we take the norm squared already inside. So this is the yellow curve over here. There are also other ones like inverse multiquadratic, which is the green one over here, which is like 1 over the square root essentially. And you can also take spline kernels, for example, which in this case here are like polynomial, and then after 1, they're just 0. So this is the red curve. Let's also see some non-examples. For example, the Laplacian kernel, also very popular, corresponds to phi being e to the minus square root r, and because it's just e to the norm. And this root here makes this phi not smooth enough for our assumptions. So we don't deal with the Laplacian kernel. And other popular kernels, like for example, the Ries kernel, very popular in our group, for example, does also not fall into this framework because it's not radial. It's not expressible as a function of this squared norm difference. Now let's see the generalization of the kernel trick to measures, which I alluded to earlier already. So we take some signed measure mu on RD and map it, as I mentioned, to this convolution, basically the integral of kx dot against mu. Yeah, so this dot means that what we get out here, m of mu will be a function in this reproducing kernel Hilbert space. Now, why do I refer to this as kernel trick? Well, recall it on the last slide, we took points from our base space, in our case RD, and mapped them into the reproducing kernel Hilbert space using this mapping x maps to kx dot. Well, however, we can also, to each x in RD, associate the direct measure at that point. This is a side measure, and we can then apply this kernel mean embedding to it. And if you plug the direct measure into this formulation, you'll see that you will get exactly also kx dot. Hence, this kernel mean embedding really is a generalization of the kernel trick from just points to collection of points or even absolutely continuous measures. We require this M to be injective, which is often referred to the Hilbert space being characteristic, and in our case is also equivalent to it being the dense subset of the continuous functions vanishing at infinity. Why is this requirement useful? Well, as mentioned in the previous slide, we do this embedding to then compare the points in the Hilbert space instead. And this is also what we want to do here. We take the measures. This is what this maximum mean discrepancy does. We take two measures and then map them into the difference of their embeddings measured in the Hilbert space norm. So we take them, embed them, and measure the difference there. And for this to be a metric, we need M to be injective, because the norm should be 0 if and only if, well, the arguments are equal. So since M is a linear mapping, it has to be injective. So this requirement gives us that this is a metric, but however, one has to be careful, and this gives some technical difficulties later also, which we were luckily able to circumvent. This metric does not make the measures a complete metric space. In fact, it's an incomplete metric space. Lastly, why is MMD nice? Well, if we square it, we get this very nice expression for it as an expectation. So it's just the double integral over the kernel times 2 times integrated against the difference of these measures. And now imagine mu and nu being discrete measures, for example. This becomes a double sum, and this is reasonably simple to evaluate as a difference between measures. For example, if you think of other difference measures for sign measures like f-divergences or Wasserstein, they are much harder to evaluate. Also, I forgot to mention, if there are any questions, please don't hesitate to interrupt. So after this brief review of kernel stuff, now let's dive into convex analysis. And the classical setting here of Rizzi and so on is we have a Hilbert space, H. This role will obviously be later taken by the reproducing kernel Hilbert space. And an F in gamma 0 of H. What does this mean? Well, F is a convex function on H, mapping into real numbers and possibly plus infinity, which shall be convex and lower semi-continuous and non-degenerate in the sense that the set where it's finite should not be empty. So it can't just be plus infinity everywhere. It's kind of boring. So what is this Moreau envelope? So this is what Jean-Jacques Moreau coined like in 1965 or 66. It's a regularization of this function. And it's defined in the following way. We have some regularization parameter epsilon, which is positive, and epsilon f is the following function. It takes an x and maps it to the value of the following optimization problem. We minimize f plus the squared norm regularization term over all x prime in h. So we have these terms that are somehow balanced by epsilon. X prime should somehow be close to x, and f of x prime should also be reasonably small. And the great thing about this Moreau envelope is that not only is this newly constructed function still convex, but it's now also differentiable. In particular, it's always finite, and it has the same minimizers as f. So, I mean, this is classical like idea behind like gradient descendant. Instead of a proximal mapping and so on, instead of minimizing f, one might instead minimize its Moreau envelope. Let's see how this looks graphically if you haven't seen this before. F is this thin line over here. You can see it has a kink. It's non-differentiable here, and in this parts it's infinite even. And the regularization, the Moreau envelope, is the thick curve, which first of all is always finite here, because Here we minimize basically this parabola, so we get this quadratic shape in the improper region, and it also smooths out this non-differentiability point, but keeps the minimizers, which is very nice. Also, we have nice convergence properties with respect to the regularization parameter. As you'd hope for, if epsilon goes to 0, the regularization goes to 0, we recover our original function, even in a monotone pointwise fashion. You can see this here. The thick line is the absolute value, which is non-differentiable, and the gray lines are the Moreau envelopes for values of epsilon, and the closer these lines go to the original function, the smaller epsilon gets. And this also makes sense from this formulation. Well, if epsilon goes to 0, 1 over epsilon goes to infinity. So when finding the minimizer of this composite objective, the first term doesn't play so much a role, and hence the minimizer will be approximately x, because minimizing the squared norm term gives us x, and hence the value of the optimization problem will be f of x. And by a similar argument, if the regularization tends to infinity, the Moreau envelope converges just to the infimum of this function. A nice interpretation from one of Stan's papers is that we can also view this from a PDE perspective, namely if we view this Moreau envelope as a function of two arguments, the regularization parameter and the input. It is a viscosity solution of the Hamilton-Jacobi equation, which is written here. So this means basically you can interpret this epsilon Moreau envelope as taking the Hamilton-Jacobi equation with initial datum f and then evolving it until time epsilon. And the function you get is then exactly this Moreau envelope. And we have this instantaneous smoothing effect. Okay, now let's dive into this third realm of f-divergences from information geometry. And these f-divergences are generated by these functions f, hence the name, and they are also called entropy functions. Let's briefly see what they have to fulfill. They have to be convex proper lower semi-continuous on R. We set all values for negative inputs to infinity. And we also require that it has a unique minimizer at 1, meaning f of 1 should be 0. And this should be the only minimizer. Lastly, a small technical condition is that we make on its growth at infinity. So we want this limit f of t over t for t going to infinity to be positive. So f should not grow of orders smaller in magnitude than linearly. And this growth is exactly this constant f prime infinity. And there should be a positive number. It can be infinity, of course, if t is quadratic, if f is quadratic, for example. Now, let's see some examples. So you can see there's a whole zoo of functions which are also in use. You might recognize some of them, and they can have quite different behavior. For example, this absolute value, the green one here, generates the chi divergence and is non-differentiable, for example. We also have this x minus 1 times ln x, which is not finite in 0. We have this x ln x, which generates the KL divergence, and you all know. And one imposter here is the red curve, which generates the Martin divergence, and it's 0 for all inputs greater than 1. And hence this this condition here is not fulfilled. So the red one is not an entropy function, all others are. And a family of entropy functions we'll look to a bit closer. And the empirical experiments are the one generated by these f-alpha functions. They're called Sally's divergences. This also is highly related to the porous medium equation. And up to like linear terms, these are power functions. And interestingly, in the limit for alpha to 1, they recover this function x ln x minus x plus 1, which generates the KL divergence. And you can see them over here. Now, finally, what is an f-divergence? One last thing before. If we have a measure mu and our target nu, we can decompose mu with respect to nu always in the following fashion. We can decompose it into this rho, which is the density with respect to nu, and mu s, which is the singular part. This decomposition always exists and is unique almost everywhere in the appropriate sense. If we have now this decomposed our measure mu like this, we can define the f-divergence of mu to nu as the following. We integrate the function f applied to the density, integrated with respect to the target measure, plus this recession constant, which, as you recall, is related to the growth of this function f, times the measure of the singular part, with the convention that if the recession constant is zero, infinity, and this part is zero, then the second term will be zero. So if we think back and only consider, for example, mu absolutely continuous with respect to nu, then the second part doesn't play a role. And here we just get f applied to the density integrated against nu. And if we now choose f to be x, ln x, for example, we recover the Kullback-Leibler divergence we all know and love. There's also a dual description in terms of conjugates, as always in convex analysis. As a reminder, the convex conjugate of f is this function f star, also defined on R, given by this optimization problem, linear term minus f for all t where it's finite. And then we can write this f divergence in this variational formulation as the supremum over a difference of expectations. This expression is very relevant for applications because often this is how f divergences are estimated, because if mu and nu are discrete measures, these expectations become sums, and you can optimize them. So we have a primal and a dual formulation, and from these we can deduce the following properties, which are folklore, I guess. Due to the convexity of f and its lower semi-continuity, this f divergence is also convex and weak star lower semi-continuous, which is like the best we could hope for. And due to this f having a minimizer only at 1, we have this divergence property, namely this divergence is non-negative, and it's only 0 if the measures agree. Now, having all of these properties now in mind, still, I hope this is how our novel functional is defined. Motivated by this expression for the Moreau envelope, let's just look at it once again. This minimum over, well, a function plus 1 over regularization parameter times squared discrepancy. We now define our MMD regularized f divergence in a similar manner. For an input mu, we want this to be the minimum over, well, this overall sigma, or measure sigma of df nu of sigma plus 1 over 2 lambda, lambda being the regularization parameter, times now the mean discrepancy squared, because this is our way of measuring distances in the space of measures. Now, this whole Moreau envelope theory is only valid in Hilbert spaces, or many properties are only valid in Hilbert spaces. We need a completeness of the space and so on. So a priori, it's not clear that this actually is a minimum and not just an infimum, and that we have the properties like differentiability and convexity that we want. However, and this is the first important result from our paper, we have this Moreau envelope interpretation. So by defining, as I did at the beginning, this extension of this f divergence to the Hilbert space by saying, well, I map a function of this Hilbert space, h, to df nu of mu, if there exists a mu which is so that h is the image of mu under this embedding, and to infinity else, as one can see in this diagram, right? So the f divergence maps measures to numbers, but we can also map them into the Hilbert space, and this gf nu is constructed exactly in the fashion so that this diagram, this lower triangle, commutes. Yeah? Taking the embedding and then doing G is the same as doing D. This extension is convex and lower semi-continuous, where the lower semi-continuity is the technical difficulty. And its Moreau envelope, concatenated with M, is our regularized f-divergence. So we have this lower triangle commuting, and when we regularize, we get the same. So this could be considered, in retrospect, the motivation for considering this function exactly, because we've now built this nice functional G. We can regularize it. It's on a Hilbert space, it's proper and LSC. And then doing this backwards is the same as our MMD regularized f-divergence. So this is very important because, as I mentioned, for Moreau envelope and Hilbert spaces, there are lots of nice properties. This is very well established, this theory. And by splitting this new functional we want into these two parts, a Hilbert space part and the embedding part, now all these properties will carry over very simply. So I mentioned this one paper which inspired us to address this problem more generally, and they at some point have quite complicated proofs, and using this a very clear, simple formula, many of their properties are now very easy to prove just by deriving them from the Hilbert space setting. The first one is a dual formulation. So you might recognize this difference of expectations we had in the dual formulation of the f-divergence. And now for a regularized f-divergence, two things change. First one is we get the squared penalty term, and we are restricted to p's which are in the Hilbert space and have to be smaller than this recession constant, but this constraint was there before, smaller than the recession constant, but restricting from all continuous bounded functions to all functions from the Hilbert space. That's the second difference. We also have a description, like a primal dual relation, that p hat maximizes this dual expression if and only if m of mu minus lambda p hat is a primal solution, which is exactly the correspondence you would have from in the Hilbert space Moreau envelope. And we also have some nice inequalities which relate this p hat or its norm and the value of a functional. Why might this be interesting? Well, as in the Hilbert space setting, and I'll say this sentence a lot now, this Moreau envelope is Fréchet differentiable on this non-Hilbert space of measures, and its gradient is given exactly by the maximizer of this problem. Hence, these inequalities here give us a relationship between the squared norm of the gradient and the functional value, which are very handy for proving estimates. You might recognize this as a Polyak-Lyajewicz inequality, only that in this case, this is the wrong way around. I'll comment on this a bit later. And we also have that its gradient is Lipschitz continuous with respect to our metric, and the Lipschitz constant is given by the regularization parameter. Now, we also have asymptotic regimes as in the Hilbert space setting. So we have gamma convergence of the functionals to the unregularized f-divergence for the regularization parameter going to 0. And for the limit lambda to infinity, we add in a multiplicative way this 1 plus lambda in front of the f-divergence, the regularized one. Why? Well, in the Hilbert space setting, I told you that the Moreau envelope converges to the infimum when the regularization parameter goes to infinity. But, well, this is in divergence, so the infimum will just be 0. So this would not be an interesting limit. However, if we add this multiplicative term, which doesn't make a difference for lambda to 0, we converge to the MMD. And this tells us that our functional balances somehow or interpolates between the f-divergence, which is nice due to its geometry, but difficult to evaluate, and the MMD, which has a flat geometry. It's a Hilbert space, but is easy to compute. So this is what the small table is supposed to illustrate a bit. We have the f-divergence. This is where we start basically for lambda equal to 0. It's positive definite, but non-symmetric, it doesn't have a triangle inequality and so on, and a variational formulation. It is related to strong convergence, has a strong topology on the measures, and a non-flat geometry. The MMD, however, is different. It's a metric, so it's positive definite symmetric, has a triangle inequality, a variational formulation again, and you can see how they interpolate between each other. But instead, it metrizes the weak convergence and has a flat geometry. So we interpolate between those two regimes and can basically get the best of both worlds. For this to happen, we need very like small conditions. For example, 0 being an interior of the domain of f star, but they are basically always fulfilled. So these are very weak conditions, I must add. And last but not least, I also mentioned this, regularizing the functional does not destroy its divergence property. It's still non-negative and only 0 if the inputs agree. Lastly, we have the metrization of reconvergence. So like the MMD, if f star is differentiable in 0, which is almost always the case, again, I mentioned this, then this mapping mu and nu to the f-divergence of mu to nu metrizes reconvergence on bounded subsets of these non-negative measures, i.e. mu converges to nu weakly if and only if df lambda nu converges, if mu converges to 0. So the last 15 minutes will be spent on the Wasserstein results. So I probably don't have to say this, but let's fix notation. We take probability measures with finite second moment, and the 2 norm being the Euclidean norm, and then the Wasserstein distance, as you all know, is the most efficient way of transporting mass from mu to nu by this transport plan pi in a horizontal and not a vertical manner. This is a bit small, but I'll explain what it is anyway. So we now need the notion of generalized geodesic convexity. So you know about geodesics in Wasserstein space, and generalized geodesics are a bit different. So here we have measures mu3 and mu2, and there is a geodesic between them, a shortest path in some sense, but we can also take some reference measure mu1 and using optimal plans between mu1, mu3 and mu1, mu2, define a different curve between mu2 and mu3, different from the geodesic perhaps. And this is then called, a generalized geodesic. And we then call a function f m convex along generalized geodesics if it's convex with modulus of convexity m, if for every such triple of measures we have this convexity. So I can't read it here. So it's f of, well, this path parameterized by between those two measures, parameterized by t, is smaller than or equal to 1 minus t times f of one measure plus t of f of the other measure minus m over 2, t minus t1, and then a squared norm term. So this is a bit of a generalization, and it's needed for existence of Wasserstein gradient flows because the Wasserstein distance does not behave as nice as we would want to along just normal geodesics. Now, the last ingredient we'll need is the Cauchy subdifferential. So, I mean, normally gradient flows say, well, I have a curve and I want its derivative to be minus the gradient of the functional at that point. So we need an appropriate replacement for this gradient, or at least subdifferential. And in Wasserstein space, this is given as follows. We take vector fields psi and L2 of mu, where mu is the point where we are evaluating, and we want in the limit nu to mu, this difference being always lower bounded by the infimum over all optimal transport plans of this guy here. So where we take the inner product on RD of psi times this displacement x2 minus x1. So this should be x1 and x2, of course. Now, we're nearly ready to now state our definition of Wasserstein gradient flows. The last ingredient we need is absolute continuity in Wasserstein space, which is very special because it's connection to this continuity equation. So this seminal result by Ambrosio, Gigli, and Savary in their green book is that such a curve is absolutely continuous, just like in the metric sense, if there exists L2 Borel velocity field of tangent vectors, basically, so that the continuity equation is fulfilled in a weak sense. And using these tangent vectors V at points T, basically, we can then define the Wasserstein gradient flows. So we say locally, and that's even weaker than just absolutely continuous curve, into the Wasserstein space with these velocity fields or tangent vectors being in this tangent space is a Wasserstein gradient flow with respect to a functional if these tangent vectors or time derivatives are included in minus the subdifferential at this point almost everywhere. And so you can think again here in two terms. One in the densities of, if they exist, of this continuity equation evolving over time, mass being conserved, or in this gradient scheme in that we start with some measure and then always go in the direction of the steepest descent with respect to this Wasserstein metric, which is defined using this subdifferential. So now to our results. Since K is a radial kernel and smooth enough, we could prove that then our regularized functional will be M-convex along generalized geodesics. So that's basically the best one can get about convexity. And we can give explicitly one upper estimate for this constant M, which is up to constant minus 1 over lambda. And then this term involving the dimension of the space, as well as the derivatives of phi. And phi of 0, which is, by the way, like the maximum value of the kernel. So you can see why radial is important. Otherwise, we don't get a certain inequality between MMD and Wasserstein distance, which we need. And we need the smoothness because, I mean, this is how we get a term like this. We can also show that its reduced subdifferential, which I introduced on the last slide, is exactly given by the gradient of the maximizer in the dual formulation. And this is also very nice because usually in the theory of Wasserstein gradient flows, one has free energy, and then we know that its Wasserstein subdifferential is given by the gradient of the functional derivative under convexity assumptions. Our energy is not a free energy, but we still have this result that the subdifferential is a singleton, and it's given by the Euclidean gradient of this maximizer, which coincides with the functional derivative. Important comment here is that while proving that it's M-convex will give us everything we need, this M seems to be very non-optimal for the following sense. So recall that if lambda goes to 0, then df nu lambda, the regularized functional, converges even in the Moscow sense, so in the sense of gamma convergence, to the unregularized functional. And the unregularized functional is 0 convex, at least if nu is nice enough. However, if we let lambda tend to 0 in this expression for M will tend to minus infinity, which is like exactly the opposite. So if we would like to get something like convergence of the Wasserstein flows with respect to the regularized divergence converging to the Wasserstein flows of the unregularized divergence, we would need these lambda convexity constants to converge to 0. But that's not what they do. So this is also still subject of ongoing discussion. We assume that there must be better estimates by some really different techniques. But as I said, it's enough for our purposes for now. The convexity along generalized geodesics gives us the existence of a unique Wasserstein gradient flow. And then, well, it satisfies this continuity equation, divergence times measure, and here the Wasserstein gradient being the subdifferential, i.e. the gradient of the maximizer of the dual formulation. And as I mentioned earlier, if the starting measure is empirical, then so is the Wasserstein gradient flow for all times t. So we can just evolve the particles over time. Now, how is this implemented in practice? Well, we have samples given from our target measure. This is our initial setting. And for whatever measure we want to start with, we take samples or just start with an empirical measure. And then we do a forward Euler discretization in time, which is a technique often used with a fixed step size, takes this form. The next iterate is given by this push forward of identity minus step size times gradient, which is the gradient of the optimizer, push forwarded the last iterate. And Pn, as I mentioned, is the argmax in this dual formulation, evaluated at gamma n. Now, if since we start with an empirical measure, also each iterate will be an empirical measure, and these positions are updated according to the following rule. This is just this formula translated onto the particles. And this is now easy to implement. One thing that's needed though is that, well, how do you compute this maximizer? So if you recall maybe this dual formulation, let's see if we can have it here. We have the maximum of these expectations and this squared norm term, which at first looks nice because, well, this looks like we could use a representative theorem and say, well, the solution P must be a linear combination of finitely many like functions kx dot in the Hilbert space. However, we have this condition here that these functions P have to be bounded by some constant, which is not natural in the setting of reproducing kernel Hilbert spaces. But we have found a way around this. And this goes as follows. Well, if this upper bound constant is infinity, as it's, for example, the case for chi-squared divergence or the KL divergence, then this is no problem. We can just use a standard representative theorem and then solve a finite dimensional problem instead. However, if this is finite, this is a real restriction, and we can't use a representative theorem. However, we've proven that if our regularization parameter lambda is not too small, namely larger than the distance of the iterate to the target, some constant involving the kernel and the recession constant, then we can still use a representative theorem basically, because this condition guarantees that the solution of the problem without this restriction must already fulfill this restriction. So in this case, in both these cases, finding Pn reduces to a finite dimensional and a strongly convex problem, which we'll then solve with just quasi-Newton method, this BFGSB. And in the case of finite recession constant, what we can do is say, well, let's say we want to use a regularization parameter of 1 over 10 to the power of 3. But at the beginning, this condition is not fulfilled. What we can do then is use some annealing strategy, meaning that we start with a value of lambda, which is high enough to fulfill this constraint. So we can use the representative theorem. And then during the flow, obviously the iterates will converge slowly, will converge over time to this measure nu. So this constant will grow smaller and smaller, meaning we can also choose our lambda to be even smaller and at some point have it as small as we want. And we've seen in practice that this works quite well. So let's see some examples. Here, this is a normal particle flow as you'd know it. The blue particles is where we start, and the orange are samples from our target. And this is now for the inverse multi-project kernel, reasonable regularization parameter and step size, and the Charlie's free divergence. Yeah, so it's of the order x to the 3. And this has an infinite recession constant. However, if we choose this parameter to be 1/2 instead of the Charlie's divergence, then we have a finite recession constant. And then we have to use this annealing strategy for this to work. But as you can see, this works reasonably well as well. Another application one might have in mind is that the number of particles that we start with and the number of samples from the target need not be equal. They don't have to have any relation to each other. So we can also use this for quantization. So start with just with very little particles, and then see how they evolve and if they recover the underlying structure. So in this case, I think you'll agree they give a pretty good picture in just with very little points of how this data set looks. Future work, there are many directions in which this can be extended. The most important ones are relaxing this assumption on the kernel, especially the differentiability is quite strong, so we can't treat Laplace kernels, for example, and definitely not Ries or Coulomb kernels, which are unbounded. Convergence rates are still open in a meaningful metric. In the Kale paper, they prove a convergence rate with respect to the homogeneous H1 norm, but this is not suited for discrete measures. So, I mean, their method goes through in our case as well, but this doesn't really tell us something we want to know. And as I mentioned, improving this M convexity estimates is an important project. We wanted to have a similar approach like this paper, where they have a Wasserstein 2 instead of MMD, but their method does not seem to work. As far as we can tell, for our case, we tried, but we didn't succeed. And then there are smaller issues like convergence of annealing strategy, replacing RD by manifolds, groups, or infinite dimensional spaces, regularizing other divergences, considering the gradient flow with respect to other metrics, or other time discretization, variable time steps, etc. So to conclude, we have created a novel objective, which is better suited for minimizing to allow sampling from a target measure of which only samples are known. Using convex analysis, our favorite topic, we gave a very clear by separating its contributions and rigorous interpretation in terms of the reproducing kernel Hilbert space. Our theory was extended from the Kovac-Leibler case to virtually all f-divergences, which can yield very interesting geometries, for example. And we've shown that our regularized objective interpolates between the nice geometry of the f-divergence and the nice computability of the MMD functional. And using this modified representative theorem I talked about at the end, we have an effective algorithm, and due to GPU parallelization, this also works reasonably fast. For everyone interested, obviously our code is on GitHub, so you can try it out if you want to. And with that, I want to thank you for your attention. I'm happy to take any questions, and for anyone interested, this is the link to the paper, and everything else you want to know is on my website below. So I hope I didn't go over time a lot. Okay.
Yeah, very good. Because I ask one small question,
Yeah, please.
So this the last image quite like the time reversible diffusion. I know the method is different, but the figures are very similar, right? I only give you samples, then you can reconstruct these samples, but it's different. They go to different sample, right?
So you mean this figure on the right?
Yes.
Yes.
Right. I mean, can you do it on image space? So far, this is two-dimensional. Can you scale this up? Yeah.
It doesn't scale well in the dimension. We have tried like 3-dimensional data sets, for example, that's fine, but in images, the dimension would be much higher. So one would need maybe to do some tweaking in the code to get it to be very fast. Because at the moment, the problem I'm having is that this BFGS doesn't run on the GPU. It doesn't run on Torch. So basically, I do all the computation in Torch, then I have to convert it, put it on the CPU to do the BFGS, and then put it back, which is very inefficient. So if this issue is solvable, then it can scale up definitely.
I see. So basically, you always want to give some samples, right, for the target. Then you want to reconstruct these samples in some sense, and you don't want to get the exactly same samples. But when you do this computation, do you go to the exactly same sample or different sample? If I go give a target in terms of sample.
So without another regularization, if I do this for long enough,
Yeah,
in practice I recover the samples pretty much exactly because I have a divergence. It has a unique minimizer, the target, and we know that the Wasserstein gradient flow is converges to the target directly.
I see.
So
This
this is also something we might improve to get like some diversity of sampling.
I see.
Yeah.
This is called the memorization. You go to the exactly same sample, you coming
Yeah,
from.
that's not what we want. So one way to easily avoid this is, as I mentioned, just choose the number of samples and starting points differently, because then you can't cover it. And in many settings, for example, I don't know, the amount of samples you can take is limited due to like money constraints or whatever, and then you can also start with very many points and have very little samples. So these are all possible.
I see, I see. So here you use the forward OLA. You don't use any special time trick. The times, I mean, for the discretization in time, it's very simple.
Yeah, it's only an Euler forward discretization, the simplest one we can think of.
Okay. Yes, we have many tricks here.
Yeah, I'm happy to hear about them. Like, if I know if you can do like Wenger cutoff of methods or something in Wasserstein space, or some splitting, maybe. I'm not sure.
We have this semi Euler method.
I see. Okay, I'm happy to hear about it.
Yes. Okay. Yeah.
Okay, very nice, thank you. Yes, sir.